Observe a projectile in flight. The motion feels completely fluid, almost entirely dictated by the forces of physics and gravity. But look closer, and you see that the arrow is actually riding an invisible geometric track. It follows a highly precise, highly predictable parabolic curve. We find identical geometric constraints scaling up to massive infrastructure. The main supporting cables of a suspension bridge, bearing millions of tons of steel and concrete, hang in that exact same parabolic shape. Even in complex cantilever structures like the Howrah Bridge, the distribution of load forces relies entirely on strict geometric frameworks to remain stable. Mathematics models all of these physical shapes using a single foundational tool, the polynomial. The shapes we observe in engineering and nature are governed by strict mathematical laws. If we understand the algebra, we can reverse engineer the structure.
To understand the curve, we actually have to stop looking at the arc itself and focus entirely on the ground. The exact points where a curve intersects the ground plane are known mathematically as the roots or the zeros of the polynomial. These specific coordinates dictate reality: the exact missile impact point, the bedrock of a bridge anchor, or a precise break-even point. This presents an engineering problem. If we know exactly where these physical anchor points need to be placed, how do we write the mathematical DNA to generate the correct curve? By manipulating the algebraic coefficients of a polynomial, we gain total control over the physical shape and grounding points of its trajectory. This diagram displays the standard general form of a polynomial. The variables, marked in one color, map the actual space on a graph. The coefficients, marked in another, act as the static settings that manipulate that space. However, you cannot just string numbers and letters together and call it a polynomial. The expression has to survive a strict structural test. We look at the golden filter rule. This requirement isolates the exponent of the variable. In this first row, the expression 3x squared minus 5x plus 7 works perfectly. Every power attached to a variable, 2, 1, and 0, is a non-negative integer. Conversely, an expression fails immediately if it contains a fractional exponent, like 1/2, or a negative exponent. The coefficients attached to the variables are free to be irrational numbers, like the square root of 5. The restriction applies exclusively to the exponents. Forcing exponents to remain whole, non-negative numbers ensures the resulting geometric curve will always be continuous and smooth, without sudden tears or breaks in physical space. Once the expression passes the filter, we locate its degree, the highest single exponent in the entire equation. This single number dictates the maximum complexity of the curve. A quadratic polynomial, locked at degree 2, can hit the ground at most 2 times. A cubic polynomial, at degree 3, is permitted up to 3 real zeros. When we plot a quadratic polynomial on a Cartesian plane, the algebraic concepts become highly visible geography. Because a zero exists exclusively where the mathematical function equals 0, the only points that matter are where the curve physically crosses the horizontal x-axis. Here, we see 2 distinct points of contact. The intersection on the vertical y-axis is irrelevant. It tells us where the curve starts relative to our measurement, but it has no bearing on the root anchor points. The real zeros of a polynomial are strictly x-coordinates. Let's isolate the standard quadratic equation. P of x equals ax squared plus bx plus c. If this curve touches the ground twice, we label those 2 exact x-intercept coordinates as alpha and beta. Those physical coordinates, alpha and beta, are bound to the algebra by a rigid coefficient lock, detailed here. The first rule is additive. If you add the 2 physical anchor points together, the resulting sum will always exactly equal negative b divided by a. The second rule governs the product. If you multiply alpha and beta together, the result will identically match the constant term, c, divided by the leading coefficient, a. The global shape of a suspension bridge, spanning miles of open water, is entirely governed by the ratio of just 3 localized numbers, a, b, and c. We can verify this lock without ever drawing a curve. Take the target polynomial, 6x squared minus 7x minus 3. By splitting the middle term, we begin dismantling the equation. Factoring the expression gives us the exact coordinates of our zeros. Alpha is 3/2 and beta is negative 1/3.
Testing the first rule, we add 3/2 and -1/3. The arithmetic sum is 7/6. We check the formula. Negative b over a is -7/6, 7/6. The physical coordinates and the algebraic ratio match perfectly. We test the product. Multiplying the roots yields -3/6, or -1/2. Checking the formula, c over a is also precisely -1/2. The derivation holds. The coordinates on the ground and the coefficients in the algebra are inextricably linked. In practice, an engineer does not start with an equation and try to figure out where a bridge will land. They survey the gorge, determine where the bedrock anchors must go, and work backward. They use the master formula. Once you know your required anchor points, you calculate their sum and their product. Plug those two values directly into this template, and you instantly generate the exact polynomial required to build the curve. Establish the two ground coordinates, determine their sum and product. The trajectory curve then draws itself backward through the air, giving you the precise path. This is exactly how the flight path in this target problem is calculated. The impact points generate the equation -x² plus 6x minus 5. The visual geometry of our world is simply the output. The algebraic coefficients are the master source code. Master how those numbers interact, and you dictate the physical trajectories of reality itself.